Okay, so today we want to start the new chapter, okay, chapter 2. Chapter 2 is about the convergent sequences, okay? And yeah, this is the part of the topics when you learn the calculus 2, okay, which is about the convergence of the sequences. And you will also see some series, okay? So now let's look at the first section, which is called the convergence of the sequences. What is the convergence of the sequences? 2.1. Convergence of sequences. Okay. So now let's consider a function, okay? So the first thing we want to define a sequence. What is a sequence? Okay, and we consider a function f. The domain of this function is the natural number. So this is the natural number set. And the codomain, it will map any number in natural number into a real number. Okay, so this is the, and f is from n to r. N is the natural number set, and r is the and n is the natural number set, and r is the rational number set. Okay. So how it maps? It will map. So any element in capital N we denoted by n. Okay. So n is, it will map. So we draw this line. So this is the means it will be mapped. N will be mapped by this function f. The image would be f of n. So every natural number, you will have a f of n. Okay. Then for the natural number n is from 1, 2, 3, 4, 5, 6, 7, 8, 9, and continue, right? So you have f of 1, f of 2, f of 3, right? Continue. So you form a list of numbers, right? And we denote this list of number, we use the braces of f of n. This n is from 1, 2, 3, 4, 5, 6, and so on, right? All natural numbers. So this list of these numbers is called a sequence. A sequence. Okay, this is the definition. So in general, we will not write the sequence as this form, okay? But keeping in mind that the sequence, okay, actually is the set of the images. But in general, we will write the sequence as we will replace, in general, we will replace this f of n with a sub n. Okay, so this is the way we often use. Then we denote this sequence by this symbol, the braces of a sub n. Right, this is the sequence we have learned in the calculus 2, right? So here this n is from 1 to infinity. N could from 0 to infinity, doesn't matter, okay? Could from 1 to infinity. And this n, lowercase n, is called the index, okay? This is called the index. And an is called the general term of the sequence, or the nth term of the sequence. The nth term or general term of the sequence. Okay. So now let's look at example. This is an example. This is a sequence of 1 over n, right? And from 1 to infinity. So here, this f, what is f of n here? F of n equals, it will map n to be 1 over n. So f of n equals 1. Sorry? Oh, sorry. It's just, I don't know why. This should be, yeah, example. Example.
Okay.
Yeah, example. Yeah, someone moved. I don't know. Okay. Anyway, I will adjust later. Okay, so this is the sequence. If you write the sequence out, it would be 1 over 2, 1/3, 1/4, and so on. Right, this is the infinite sequence. Another example, which is the yeah. Okay, so the next one is the sequence, which is called the recursive sequence. Is this the first time?
Yeah, I think
And
so.
it's never before, right? It never happened before. Okay. So recursive sequence. So recursive sequence is the sequence that's determined by the first one, first item. Okay, first number. And also we have the relation between the an plus 1 and an. Okay, so this is the one example, which is called a recursive sequence. So this is a1, we're given a1 equals 1. Then we can determine, we use this relation, an plus 1 is determined by an, the previous one, okay? So this is the cases, that is the an plus 1 over n. If a sub n square is less than or equal to 2. Okay, a sub n minus 1 over n if a sub n square is greater than 2. So this is called the recursive sequence. So this is the a1 is given, the first number is given. Then the next number, the following numbers are determined by the previous one. Okay, so if you plug in a1, okay, the a1 square, we need to use the criteria. Which one we should choose, or with 2 branches, which one we should choose? So we check the conditions that a1 square equals 1, which is less than 2. So we take the first branch. Okay, so this is the a1 equals 1. So what is a2? a2 equals, so which one we should use? Since a1 square is equal to 1, so less than 2, less than or equal to 2, so we take this one. All right, we take this one. So this becomes a1 plus 1 over 1, right? N equals 1 here. So this is equal to 2. Okay. Then what is A3? A3 is determined by A2, right? So here, N equals 2. So it's determined by A2. So we need to look at A2 is given by 2. So which one we should use? We use this 2 conditions, okay? A2 square equals what? 4. 4 is greater than 2, so we use the second branch. So we use this is A3 equals A2 minus 1 over 2. So which is 2 minus 1 over 2, which is 3/2. Okay? So the 3/2, so A4, for example, A4. A4 equals what? Which one? The top one, the upper one, or the lower one? The top one? The top one is means what? How do you determine it's the top one? We need to check what? We need to check A3, right? A3 square, right? A3 square, which is 9 over 4. 9 over 4, so it's greater than 2, right? So which one we should use? The lower one, right? So this is the A3 minus 1 over 3. So this is 2/3, 3/2 minus 1/3, so which is 7/6. Right, then you continue this way. Okay, then you can generate the next term. So this is called a recursive sequence. Let's look at another example. So now let's define a new sequence. Sequence we denoted by S of n, by the following way. S of n is equal to the summation k from 1 to n, r to the n, r to the k, sorry, r to the k's power. So this is the, so Sn is given by this formula, okay? So let's look at let's look at different cases, okay? If r equals 1, so this is the sum of the geometric numbers, right? If r equals 1, then S of n equals n. So the sequence is actually this one, right? If r is not equal to 1, so we can use the geometric sum, okay? So S of n is equal to what? Equals, if this is the case, this is the r is not equal to 1. So this is the r plus r squared, right? Plus r to the n. This is the geometric sum. So this one is equal to 1 minus r times 1 minus r to the nth power. Okay. So the sequence would becomes this one. R 1 minus r n to the n over 1 minus r and the braces. So we always use the braces, means it's a sequence. Okay. So you can use this way to define new sequences, okay? So remember that this. Okay, so this is the, so now let's look at the remark for this one. Or before that, let's look at this one. This one is actually, this Sn is from a new sequence, which is generated by a new sequence, which is r to the nth power, right? N from 1 to infinity. This this one, right? Sn is the first n terms to sum up, right? So S1 is the first term. S2 is the first two terms, the sum of first two terms. S3 is the sum of the first three terms, right? Okay, so this Sn is from this sequence, okay, to form a new sequence. We can use this way to form a new sequence. So this is the thing, the remark to, this is the remark. Remark says, okay, we have the given a sequence C sub n. Okay, this is given. We can define a new sequence. Let us define a new sequence using the way we just said before. And in the example, new sequence, which is denoted by Sn, S sub n, using the following way by S sub n is equal to the summation of the first n terms. So this is k from 1 to n. Right? The sum of the first two terms, first n terms in this sequence, in a given sequence. So this Sn, then we can form a new sequence, Sn, right? This Sn is called, this S sub n is called what? The nth partial sum. Partial sum. Okay, so you should know this kind of terminology in the calculus too, which is called a partial sum, the first n terms. Okay, take the sum. It's called a partial sum. So sometimes we just say partial sum, okay, or the nth partial sum. Okay, and we have another one, which is, so this is the finite sum. If you form this one, infinite sum, okay, because this sequence has infinitely many elements, right? If you add them up, so this will form an infinite sum. This infinite sum is called what? Infinite series. Sometimes we just say series. Infinite series. Okay, sometimes we just say, okay, series. The series is nothing but an infinite sum of a sequence. Okay, an infinite sum of sequence. Okay, so this is something we have learned in the calculus too, right? Some definitions, so just a quick review these definitions. Okay, so now let's look at the following things. So in the calculus, we often say, okay, we have a sequence, okay? This sequence converges or is converges to a number A, right? In the calculus 2, we know that means the limit of an equals A, right? In other words, the limit n approaches infinity of an equals A. Okay? So what does this mean? This means when n is large enough, it's very large, okay? Then this, when n is very large, then this an, after that, all the an should be very close to A, right? Okay? Or the difference between an and A is arbitrarily small, right? If n is large enough. So this is called convergent to that number, right? It should be very near to this number A, right? When n is large enough. Okay, so but this statement is not precise. Okay, so we want to get a precise definition for the statement that says, okay, what's the meaning for the sequence of A sub n converges to A. What is the precise definition? Okay. So now let's look at the definition. This is the definition. Okay, so this definition, it took about 2 centuries to know the precise definition for this convergence. Okay, for a sequence, the convergence of a sequence. So now let's look at, we say, okay, this definition, a sequence A sub n is said to be convergent to a number A if, this is convergent, okay, if for any epsilon greater than 0, this epsilon could be arbitrary small number, there exists an n which is a natural number, okay? This n is greater than 0, okay? There exists an n. This n should be depending on the choice of epsilon, okay? Depending on the choice of the, for any epsilon, you must have the corresponding n. So I use this parenthesis of epsilon. That means the n is depending on the choice of. So sometimes in most cases you will not have this. You just say, okay, n. Okay, there exists a capital N, n is greater than 0, which is an integer. Okay, such that the difference between a and a is less than epsilon for all n greater than capital N, or greater than equal to greater than, doesn't matter. Okay, so that means, so how can we explain it? Okay, so for any epsilon greater than 0, so you can take epsilon arbitrary small. Okay, very small number. Now for this epsilon, when you choose an epsilon, a small number, then you can determine a capital N. After the index, when the index greater than equal to this capital N, so it means the terms after a capital N, okay, like a sub n, a n plus 1. After that, the difference between the elements in the sequence, which is a sub k, sub capital N plus 1 and so on, between these elements at A is always less than this small number. So it means after that, it will be nearby. Okay, it would be a nearby. So now let's look at the graph. Okay, the graph for this for the understanding for this one. So this is the one thing I just want to erase. So now let's look at the remark. First one. So now let's look at what's the meaning for this one. This is the, let's get rid of the epsilon, the absolute value sign. So that is what? That is a sub n should be between a plus epsilon and a minus epsilon. Okay. So this is just the definition of the absolute value, right? So from the graph, okay, if this is the A, this is the A plus epsilon. This is the A minus epsilon. No matter how small epsilon is, you can always find this capital N such that after capital N, in other words, an plus 1, a sub an plus 1, an plus 2 are all in this interval. You can see we can choose epsilon is small, very small, so it will be very close to A, right? But for no matter what, how small it is, you can always, for each epsilon you choose, the small epsilon you choose, you always can find this capital N. After that, okay, after the index, after that, this is an plus 1, an plus 2, an plus 3, all the members in the sequence will be inside this interval. Because this is the infinite sequence, right? You have infinite many members. So all the members is inside this interval, no matter how small this epsilon you choose. So that means an is convergent to A. The sequence is convergent to A. Okay. In other words, if you have this one, if you have A, okay, this is the A epsilon, okay, this is A minus epsilon, this is A plus epsilon. So we say a sequence is convergent to A, so that means when N is large enough, how large enough is large enough? We can find this capital N, right? If N is greater than or equal to this capital N, then all the sequence will be in this interval. Maybe outside, you have finite terms outside, no problem. But after that, all the terms in the sequence would be in this interval. Outside, there are finite terms outside, doesn't matter. Okay, we don't care about the finite terms. We only care about after that, all the points would be inside. So this is called convergence. Okay, it will be very close to A if N is large enough. Okay, so this is a very important definition. So now let's look at some comments and remarks. So this is the first remark, which is the geometric meaning. Okay, you can see this, the absolute value of an minus A is less than epsilon, which means an is A minus, between A minus epsilon and the A plus epsilon, right? So which is the center, which is the interval with the center A. Okay, the radius is epsilon. So the second remark. Okay, the second remark says, okay, the convergent, a sequence, if this sequence is convergent, it must converge to a one number, not more. You cannot converge to two numbers, okay? More than one number. So the sequence cannot converge to more than one point. Okay. That means there's no convergence, not convergence. So we have no number we can converge to. If you have if the sequence is convergent, it must converge to a one number, a one point. Okay, so we want to prove this one. So the proof, I will show you the proof here because this proof contains some technique you will see in the future. Okay. So since the problem said, okay, it cannot converge to more than one. Okay, so let's use the what contradiction, right? It cannot. How can we say it cannot? Okay. Well, let's just use the contradiction. Okay, so we suppose it can converge to two numbers. Okay. Suppose the sequence converges to A and A prime. And here, A and A prime are not the same thing, okay? Where A and A prime are not equal. So from based on this one, we want to derive some contradiction. Okay. So here, A and A prime are arbitrary, are two numbers. So we must have the order, right? Which one is bigger, which one is smaller? Let's determine, and let's just say, okay, do the assumption that without lot of generality, we assume that A is less than A prime. We can do that, right? We can do that. So now here, I want to talk about the idea for this one. So this is A. This is A prime, right? So if a sequence A sub n converges to A, so that means you can choose some epsilon there for any epsilon, right? It would be A minus epsilon, A plus epsilon. There is a capital N. After capital N, all the terms, all the numbers would be inside this interval. This is called this convergent to A, right? Convergent to A. So convergent to A prime. So the same epsilon. This is A prime minus epsilon. This is A prime plus epsilon. There is another capital N. After that, all the points will be here. Okay? So you can think about, at last, all the points will be here. At last, all the points will be here. It's impossible, right? You cannot say, okay, all the points in this interval and all the points in this interval, because you choose this epsilon. Epsilon is arbitrary. We can choose epsilon, right? We can choose this epsilon to make these two intervals to be what? No intersection, no common parts, okay? Independently as well. There is no the intersection of these two intervals to be empty set. If you choose epsilon is have their common parts, we cannot say that, right? You can always have some inside in both intervals at the same time. But if you choose epsilon to be small enough, then we can separate these two intervals. Then you will see, when n is large enough, all the terms in the sequence will be here. When n is large enough, all the terms in the sequence will be here. So that would be the contradiction, because we choose this epsilon is small enough to make these two intervals to be separated. Okay, there is no common parts. So that is the idea. But how do we write in the math language? Okay. So what epsilon we want to choose? So the distance between these 2 points is A prime minus A, right? If we choose epsilon to be A prime minus A divided by what? Then these two intervals would be separated. Divided by 2, right? Half distance. Okay, we can make it even smaller. Let's say, okay, it's 4. Right? Make it even smaller. Doesn't matter, right? Epsilon could be any number. In the definition, we say, okay, this epsilon is arbitrary epsilon, right? Arbitrary epsilon. So we can take this epsilon to be this number. Then we can separate these two intervals. Okay, so now let's continue. Let's write this is the idea, okay? So we take this epsilon is a prime minus a divided by 4. Okay, so this is this red color should not be in your proof. Okay, this is just some ideas. I just say, okay, idea. These are just some ideas. Okay, on your scratch paper. So we take this epsilon to be this number. So you can see this is not mystery number, right? This is the number we are choosing from the graph, right? But when you read the proof, okay, the textbook said, okay, we take epsilon to be this number. So you may be curious, where's this number from, right? But actually it works, right? At last, when you read the proof, you will see that. So this number is from here, okay? Is from the discussion here. So it's called analysis. So we do the analysis for this problem, right? So it's called an analysis course. So this epsilon we take here, you can take over 6, over 2, over 8, doesn't matter. Just separate it, okay? Just separate these two intervals. Okay, so we take this one. So since we know this a sub n converges to A. So by the definition, there exists a capital N. We use the capital N sub 1, which is greater than 0, okay? Such that when n is greater than or equal to capital N sub 1, this is the distance between A and A is less than epsilon. So this is the definition, right? When n is greater than this capital N sub 1, then after that, all the distance between A and AN would be less than this epsilon. This epsilon we take here, okay? So now let's look at it because it converges to another point, right? Since A sub n, the sequence converges to A prime. So what does this mean? This means we have another n, we denoted by n sub 2, greater than 0, such that when n is greater than or equal to capital N sub 2, an minus a is a prime, a prime should be less than epsilon. We still take this epsilon, okay? So the next thing is we want to use these two inequalities at the same time. So there is a technique we will use here, trick here, okay? After n sub 1, it will be, this one would be true, right? After n sub 2, this time, this inequality would be true. We want to make these two inequalities to be true at the same time. What we should do? Let's take this capital N to be maximum of n sub 1 and n sub 2. Let me take the maximum number of these two numbers. Then, when n, the index is greater than or equal to this capital N, an minus a is less than epsilon. Of course, it's greater than this maximum number. Of course, it's greater than n sub 1, right? Because n is the maximum of an n1 and n2. So it's greater than the maximum. Of course, it's greater than n1. So this inequality would be true. The same thing, since it's greater than this maximum of n1 and n2. Of course, it will be greater than n2. So this inequality would be true. And this an minus a prime is less than epsilon. So you see, we take this capital N to be the maximum of these two, n1 and n2. Then we have, and when n, the index is greater than this capital N, the maximum number, then these two inequalities would be true at the same time. Okay, so now we can use these two inequalities. So in other words, i.e., this is the an should be between a minus epsilon and a plus epsilon, right? This inequality tells you the center is a, the radius is epsilon. And also an should be also in this interval, a prime minus epsilon and a prime plus epsilon. This is for n is greater than or equal to this capital N. Okay, so you see all the terms after capital N would be in these two intervals. So the next thing is we want to show these two intervals as there's no common parts, are separated. Okay, are separated. So how to, let's calculate, let's plug in epsilon, right? So however, we know it must work because of the way we choose epsilon, right, from the graph. So we just say, okay, what is a minus epsilon and a plus epsilon? If you plug in, this is the a minus, this is the a prime minus a over, we choose 4, right? Yes. And a plus a prime minus a over 4. So if you do the calculation, it would be 4a, 5a, right? 4a, 5a. Minus epsilon, so it's the, yeah, 5a. Yeah, I made a mistake here. 5a minus a prime over 4. Comma. So this is the 3a plus a prime over 4. And a prime minus, let's look at another interval. So this is the a prime minus a over 4. This is the a prime plus a prime minus a over 4. So this interval would be, this is the 3 a prime minus a plus a over 4. And this is the 4, 5 a prime minus a over 4. So these two intervals, this interval and this interval.
Minus a over 4?
Which one?
Would the first one be minus a and the second one plus a?
Minus plus.
Oh, yeah.
Yeah, so here, yes, this should be plus here. No, this is minus. Sorry. Yeah, this is minus because here is the first term. Okay, so the next thing is, okay, since a prime is greater than a, so obviously this number is greater than this number, right? Because there is a 3 times a prime. There is 3 times a, right? So this number is smaller than this number. If you don't believe it, you just take the difference to see if it's positive or negative, right? So, but here we can conclude that because This is the way we choose, right? This is the way we choose. We know it must be separate, right? It must be separated. So since these two intervals, this is the 5a minus a prime over 4, and this is the 3a plus a prime over 4 intersects with this is the 3a prime plus a over 4, and this is 5a prime minus a over 4. This intersection is empty set. So this causes the contradiction. So there is a contradiction, right? Contradiction to what? To this result. We say when n is large enough, greater than this capital N, after that, all the points a and would be in these two, in both intervals. But these both intervals are separate, so it's impossible. All right, impossible. So what's your conclusion? Where is this cause from? The problem cause from this one. This is the a is not equal to a prime. If a equal to a prime, no problem, right? Because these two intervals will coincide each other, right? So a is equal to a prime. So that means if it's convergent, it must converge to a point. One point. Okay. So this proof tells you a lot of things. Okay. The proof tells you a lot of things. The way we often prove for our in this chapter. Sometimes you can pick this epsilon, right? So the first thing you need to do is you need to do some analysis on your scratch paper, right? You can pick some special epsilon to make the thing to be work, okay? To make the thing work. So then sometimes you will say you have some capital N1, for this one is true, the capital N2, for this one is true, but we need these two to be true at the same time, so we need to take the maximum, okay? So this is the technique you will use here. So this mystery number is not a mystery at all, right? It's just from our analysis on the graph here, okay? So now let's look at some notations. The third remark. This is the second remark. The third remark. If a sequence, this is just some terminology, okay, converges to a number A, then we call this A is called the limit of the sequence A through N. We write it as the limit n approaches infinity of A through N is equal to A. This is just some terminologies, okay, we already used in the calculus 2. But here I just want to see this one. So the definition also gives you the definition of this convergence of sequence also gives you the definition of this limit. So in other words, i.e., the limit n approaches infinity of an equals a. So this is the limit, right? What does this mean? It means for any epsilon greater than 0, there exists the capital N greater than 0 such that an minus a is less than epsilon for all n greater than equal to this capital N. So you need to memorize this definition, okay? should be very familiar with this definition. So the meaning for the limit an equals a when n approaches infinity, which means this epsilon is greater than 0, and there exists for any epsilon greater than 0, there exists a capital N greater than 0, such that this an minus a is less than epsilon for all n greater than equal to that capital N. Okay, you should be very familiar with this definition. Remark 4. This capital N depends on the choice of epsilon. Okay, for each epsilon, you will have the different capital N. So actually, this capital N is a function of epsilon. Right? For different epsilon, you will have the different capital N. Okay, so now we want to use this definition to prove some results. Okay, not results, but okay. The first one is the example. Okay, example. The example, we want to show that this limit is equal to 0. In other words, this sequence converges to 0. Okay. To prove. We just pick arbitrary epsilon, let epsilon is greater than 0. Arbitrary epsilon. Okay, when we pick the epsilon, that means epsilon is fixed. Okay, no matter how small it is, it's fixed. We pick an arbitrary small number, epsilon greater than 0. So the idea is the following. I just want to use different color. Okay. Want to use this color to tell you the idea. So we need to find, you can use a box, okay, here. We need to find this capital N, right, such that 1 over n minus 0, take the absolute value, is less than epsilon for all n is greater than or equal to this capital N. Right? Okay, so how to find it? So this one, this is the true, right? This is the absolute value of 1 over n. N is greater than 0, so it should be just 1 over n less than epsilon. If n is greater than capital N, so this one must be true. Lowercase n is greater than the capital N, right? So the denominator is smaller. Sorry. It's not the case. So this is our aim, right? So we know that 1 over n is less than or equal to, because n is greater than or equal to capital N, right? So 1 over n should be less than or equal to 1 over capital N, because the denominator is smaller, so it's you have a larger fraction, right? If this 1 over epsilon is less than 1 over capital N is less than epsilon, then we will get this result, right? We will get this result. If this is true, then we will automatically have 1 over lowercase n is less than epsilon. Then we are done, right? So we want to use this one to determine our capital N. So capital N is, let's solve for capital N. Capital N is what? N is greater than 1 over epsilon, right? We solve for capital N. So you 1 over, right? So let's you change the direction or multiply N on both sides and divide by epsilon on both sides because both are positive numbers, so no problem, right? Then you will have this one. Okay, we just take an N which is greater than epsilon, 1 over epsilon. An integer greater than 1 over epsilon. Then we are done, right? We use this capital N. So now here we take this N to be, we use this one to remember what this symbol means. It means the smallest integer greater than 1 over epsilon. Okay, you can, of course, you can plus 1, doesn't matter which one you want to use. Okay, you can plus 1, plus 2, right? You just choose a capital N, which is greater than an integer. Okay, positive integer is greater than 1 over epsilon. So here, for our convenience, we just choose, okay, we take this. This is called the greatest, the least integer, the least integer greater than 1 over epsilon. Okay, the least integer greater than 1 over epsilon. If you take n is equal to this number, then 1 over n automatically is less than epsilon. Then we are done. Okay, so this is the discussion here in your on your scratch paper. So how do we this number from? Where is this number from? It's from here, right? The discussion here. We want this one to be true. We also want this one to be true. The same thing, right? These two are the same thing. Because 1 over n is a positive number, so absolute value doesn't matter. We want this one to be true. If we can make this one to be true. Right? The reason is n is greater than or equal to the capital N. So 1 over n is less than or equal to 1 over capital N. If we can make this one to be true, then we have this one automatically. Right? So to make this one to be true, so this one you see, we can solve for n. This is the thing we are looking for. We're looking for this n, capital N, an integer. To make this one to be true, so we solve for n. N is greater than 1 over epsilon. So we take n to be the least integer greater than 1 over epsilon. If we take this n, then everything would be very straightforward. You can go back. Okay, go back to here and then go back to here. So this is the way we think about how to prove. Okay. Okay, so now let's go back to our proof. Okay. So we say we let epsilon to be greater than 0. So this epsilon is arbitrary, right? So there exists a capital N which is equal to the least integers greater than 1 over epsilon. So this is greater than 0, such that when n is greater than or equal to capital N, so 1 over n minus 0, we want to show this one is less than epsilon. So let's do the calculation. This is 1 over n, right? This is less than or equal to 1 over n capital N, right? 1 over capital N. 1 over capital N, which is what? Capital N is equal to 1 over the least integer greater than 1 over epsilon, right? So less than, because we can shrink the denominator to be 1 over epsilon, right? This number is greater than this number. So the fraction would be smaller, right? Oh, what's that? What is this epsilon? Okay, We're done. Sorry, there is no equal sign here. Okay, so this is the end of the proof. We just do the calculation, we notice that, okay, it's less than epsilon. So what does this mean? This means this one. Okay, let's summarize it. So let's look at the definition, okay. The definition says, okay, if an is approaches a, the limit of an equals a, that means that for any epsilon greater than 0, there exists a capital N greater than 0 such that when n is greater than this capital N, an minus n less than epsilon, okay. So do we have this one? There exists for any epsilon greater than 0, we'll pick an arbitrary epsilon, there exists the capital N, which is determined by this one, okay. When n is greater than capital N, 1 over n minus 0, take the absolute value, is less than epsilon, which is exactly the definition, right, for the limit of a sequence. Exact definition. So when you are asked to prove the limit of a sequence, so this is the way, a very typical way, okay? For any epsilon, you try to find this capital N. Maybe the different students, you have the different capital N, no problem, okay? You just need to make, when n is greater than this capital N, 1 over n minus 0 is less than epsilon. If you can make this inequality to be true, then we're done. Okay, if you here plus 1, plus 2, it doesn't matter, you will still have this inequalities. Okay, you will still have this inequalities. So this number, you can see from our proof, this n, capital N, is depending on the choice of epsilon, right? For the different epsilon, you will have the different capital N. Right, so this capital N depending on epsilon. Okay, they have the dependence between the n and the epsilon. Okay. Now let's look at another one. Do we have time? Yes, we still have. Okay, we can stop here. Okay, next time we will continue. So since we just start, so we have no homework, okay, for this section yet. Next time we will try to finish. Yeah, maybe we cannot finish yet, but yeah, I will try. We can slow down, okay, we can slow down. Any questions for the online students?